given here. Okay, you just put 1 between I and j for the complement if there was a 0 for the initial binary relation. Okay, so it's very straightforward. So in terms of rational matrices, x tilde for equivalence relation is given by u minus vol x. Okay, where vol u is the matrix full of 1. So this is for equivalence relations. For other relations, I take the opposite of x, not the complement, but the inverse relation. Okay? So the general term is given here, but typically it's just the transpose of the relational matrix vol x. So to give you an idea, if my order relation is lower than, then the inverse relation is greater than. Okay? So just for illustrating those different ideas, so here is the rational matrix vol x of the previous example, and since it's an equivalence relation, in that case we have the opposite, which is the complement. Okay? And for the other example, for the order relation example, the x tilde is given here by the inverse x ring. Okay? Now is the formulation which gives another view of Kendall gamma and which uses relational matrices. So what we can see here is that we have used, okay, we are given two binary relations or two variables of conjugate. We take the rational matrix and we compute the opposite. Okay? So those two elements, I mean vol x and vol y, are given. What I introduce here as parameters are the new variables. Okay, so what are the new variables? So for all ij, new ijx is typically a non-negative weight that I assign to the relation ixj. Okay. And for new tilde, it's for the opposite. I mean, I give a weight to the relation ix tilde j. So those weighting schemes, they are important because they are the parameters that allow us to make the difference between two different association measures. And another feature which is interesting is that, as I'm going to show it on the next slide, those weighting schemes can be also expressed in terms of the rational matrices. Okay, so they are all data dependent. So using this formulation, I can recover for equivalence relations different association measures. So of course we have T, the Johnson-Berzelius index, Brown's index, which is also related to the Condorcet criterion, and also Pearson's correlation coefficient, in that case taken on the 4-4 table. Okay, so as you can see, each of these association measures are given as a particular case of the previous equation, when we set the different weighting schemes given by the second and the third columns. So this is for equivalence relation. So again, in that case, I take the opposite, x tilde, as the complement. We can use the same formula, but for other relations. So in that case, x tilde is x real, I mean the inverse relation. So in that case, we have the particular association measures. So if we have the uniform weight, we recover Kendall's tau A, and here we have Spearman's rho A. So again, here all the different weights are given in terms of the relational matrix. Okay, so indeterminacy, so we talked about this fundamental concept previously, but typically it's when there are as many agreement pairs than disagreement pairs. Okay, so in this formulation of lambda, we can see that there are another kind of concept, which is weighted indeterminacy division principle. And if we look at the numerator of the previous equation, and if we look at when it equals 0, we can see that we have this identity. So lambda will be equal to 0 when the weight here associated to positive agreements plus the weight associated to negative agreements equals the weights associated to the different disagreements. Okay? So we can see that in our formulation, the weighted indeterminacy deviation principle is what allows us to have the semantic between positive and negative values. Okay, so it's null when we have weighted indeterminacy, and of course it's positive when the weight of positive of agreements is greater than the weight of disagreements. And of course it's negative otherwise. So this was a new approach for interpreting Kendall's general coefficient gamma. And now I'm going to focus on heterogeneous binary relations, and I will propose an extension of this coefficient. First, I will give you some example of what I mean by heterogeneous binary relation, and then I will show you that we can extend this coefficient from a geometrical perspective, which will lead us to the definition of similarities of order T. So, given two equivalence relations, so as I said beforehand, I assume that there is an heterogeneity between these two equivalence relations as soon as the number of categories is different or the distribution among the different categories is different. So these are two examples. We can see that X here has 3 categories, while Y here has 2 categories only. Okay? So for order relation, since there are different kinds of order relations, when you want to compare, for example, here a linear order or total order against a pre-order, then we have to pay attention to this heterogeneity. So in that case, here again X is a linear order, Y is a pre-order because you have A, B, C which are type. So how can we take into account this information? So in particular, these examples show that somehow heterogeneity is related to the difference between the densities of one of the rational matrices. So this is the intuition behind this kind of extension. Okay, so how to deal with heterogeneity? So in this one, we propose to extend lambda and we define similarities of order T. So to introduce all those concepts, I will start by giving the definition of what I call weighted symmetric relational matrices, in short WSRM. Then I will interpret those objects in an Euclidean space, okay, where I will use the Frobenius scalar product. And then I will argue that heterogeneity between two binary relations is related to the difference of the norms of the WSRM. Okay? And I will show that lambda is not capable of dealing with such heterogeneity properly. So I will extend this coefficient and I will introduce the similarity of order T. So what I mean by weighted symmetric relational matrix is just the definition of the straight X here in our context. So typically is the weighted relational matrix minus the weighted opposite, the weighted relational matrix of the opposite relation. Okay? So it's just a way to simplify the notations. Obviously, we can interpret WSRM in the vectorial space. Okay, the vectorial space made of real valued square matrices of size n. Okay, and in this vectorial space, I am taking the Frobenius inner product, which is recalled here. So, using those notations, we can see that lambda is given by this equation. So, obviously, we have the Frobenius norm here, and of course, lambda is the cosine of the angular measure between the vectors x and y. I mean, straight x and straight y. So we argued previously that heterogeneous equivalence relation or order relations have a difference with respect to their densities. So in terms of WSRM, intuitively, this difference is with respect to the norms of the different WSRM. As we can see in this formulation, lambda is typically the cosine of the angular measure between those two vectors, and it is only based on the angular measure. Okay? So here we do not take into account the difference between the norms of WSI. So I propose this generalization, okay, of lambda. So the important thing here is that at the numerator, I have introduced the generalized power mean of order T, whose definition is recalled here. And we can recover the previous case as a particular case of this generalized mean. So typically when T tends to 0, we recover the geometric mean. And in that case, in particular, I recover the lambda similarity measure. But the interesting thing is that we have a whole family of similarity measures, so we can make T different from 0. We can take T equals 1 and T tends to infinity. So we have different mean with respect to the different values of T. So in that case, we have lambda. Since I don't have a lot of time, I will go directly to the main point. Okay, so using this formulation, I introduce now two geometrical features. The angular measure that we saw earlier, but also a new one, which is gamma. Here, it's the norms ratio. Okay, so gamma is given here. It's the difference, it gives us a kind of difference between the norms of the vectors. So we can show that ST, given previously, can be expressed using those two geometrical features. Okay, we have the cosine as the numerator, and here the generalized power mean at the denominator. So the important thing is that I'm going to show you on the graph directly. So here, let us look at the graph on the left-hand side. So here I took the cosine equals 1. What I want to show you is that now that I introduced gamma, it's an interesting feature to take into account heterogeneity. So typically here on the x-axis, I make gamma vary from 1 to 2. So the greater gamma, the bigger the difference between the norms. And I plotted different ST with different values for T. So S0 is this line, and we can see that it is independent of gamma. It's the cosine. Here the blue line is when T equals 1. So the interesting thing here is that, we can see that as gamma varies, the similarity value decreases. Okay? And this is stronger when T is greater and greater. Okay, so this is the intuition. We have different properties for this similarity measure, in particular with respect to axioms that we are given as a similarity index. One important thing that I wanted to tell you is this following theorem. When T is non-negative, then the square matrix of generator STXY is positive semi-definite. Okay, so we have an Euclidean matrix behind those similarity measures. So the proof is based on Gershgorin circle theorem. So if you want, we could go back to the question about the theorem. Another interesting feature of this similarity measure is that it can be expressed in terms of the scalar projections. We have two vectors. We can project one vector onto the other one, and the scalar projection is a kind of similarity measure between those two, but we can also take the projection of the other one onto the first one. So we have two scalar projections, and we can show that this ST measure is given by this formula. Okay, we can again use here the generalized power mean. Just a simple example to illustrate that it works. So typically I took three variables, x, y, and z. So we can see that x and z, they have the same densities, while y has a different number of categories. And different density. So I took the weighting scheme related to the true prose coefficient, and I computed the WSRN. I computed the norms, and we can see that the norms of X and Z are the same ones. Okay, so they are not heterogeneous. In contrast, Y has a distinct norm. So when I take the cosine measure, I have those following values. Okay, and when I make t equals 1, of course, X and Z, the value doesn't change because the norms are the same ones. So there is no effect of gamma here. But for X and Y, since they have different norms, we have a similarity value which decreases. Okay? And when t equals 10, we have this value. So the interpretation is important here because using the cosine, which is a very used coefficient, we can see that here the cosine says that y is more similar to x than z. And if we start penalizing, the norm, and if we use t equals 10, then we have the over ranking. Okay. So rapidly, future work. So the next step will be to use this similarity of order t to, for example, cluster heterogeneous ranking data, or do multidimensional scaling for heterogeneous valuation, because we have shown that we have an Euclidean matrix, so we can use all the tools developed in data analysis to treat heterogeneous binary relations. So here are some references. Sorry for being long. And thank you for your attention. If you have any questions,